Hi, everyone. Good morning. How are you? Fine? Woohoo! We are not that much, but we are very good. So, thank you for being here today. My name is Nuno. I'll be talking a bit about load testing. So this is the subject of my talk, a little bit about me. I'm currently an engineering manager and cluster lead at Farfetch. But I've made my way through all these companies, Talktest, Siemens, Create IT, and Link. So here are the links where you can reach me, so feel free to reach me in anything you need. So, little quiz. Who here has applications that are running on the internet? Okay, so a couple of people. And how many of these applications do have performance metrics collecting live? So do you guys know how many requests per second your application is performing? Okay, so a lot less people, 3. And before pushing those applications to production, do you load test them before going live? Okay, couple-ish. Okay, so let's start by defining what load testing is. So this is the definition from Wikipedia. So, and I pretty like this definition because it's generic enough and concise enough. So load testing is a process of putting demand on a software system or computing device and measuring its performance. So there are 2 parts of this sentence which are very important. The first one is putting demand into the system. The second is measuring its response. So we are kind of, when we are load testing a system, we are interested on looking at how our system will respond to load and if it will scale, what's the scaling curve. But what does demand mean? And the answer is everything it depends on your system, right? So if we are looking at a web application or web API, demand means HTTP requests. If you are working on a database system, your load is queries, right? If you're working on a message broker, your demand is message. And if you are, for instance, developing an application that reads CSV files or XML files, your demand could be more files or bigger files. So demand really varies on the type of application that you are developing. So what's the common strategy for performing load tests? You pick up your application and you push load into it, and you collect metrics. And then you interpret those metrics, and if those metrics are not what you expect them to be, you go and you find bottlenecks on your application to see where the slowness is coming from. You apply fix and then you iterate. You keep testing and collecting and iterating on your application until you're happy, and then you can go and grab a beer. Regarding infrastructure, there are several setups that we can use for load testing. The simplest one is to run the load tests on our development boxes, which is what I'm about to do here. So in this scenario, you have, I'm going to focus on JMeter because JMeter is a tool, open source tool from Apache to generate load and collect metrics. I'm going to focus a bit on JMeter, but there are other tools that you can use out there. So on this setup, you can have JMeter running on your box, the application running on your box, and the database running on your box. So this is the simplest case. And believe me, there are lots of things you can do with this setup, and you can find lots of stuff. Then if you want to run load tests on QA, you have to go to a more complex scenario where you have one box generating the load, another box running the application, and another box running the database. And this will allow you to test a scenario that is closer to the production scenario. But we can take it further, right? Usually our applications running on the internet don't run on a single box. We have clusters and several nodes running the application, and then you can scale the load testing scenario to this scenario, where you have several boxes running the application and the load balancer in front of them, just sending requests to every node. And you can generate load against the load balancer and test how the cluster will handle the load. But you can come up to a point where a single box is not enough does not generate load enough for you to saturate the system. So you probably will need to scale also the load generation to have multiple boxes generating load to be handled by the network, the load balancer. And JMeter actually supports this scenario where you can have several agents generating the load and having a third node or to orchestrate the entire load generation process. So this is supported by JMeter. It's also supported by Visual Studio Enterprise or Ultimate. It also has this kind of setup where you can generate load in cluster. So about metrics, what kind of metrics should we be interested in collecting? And once again, it kind of depends on your application, but there are a common set of metrics that it's basic usage. So it's also important to collect some metrics on the boxes that are generating the load. And in this case, we are interested in usually computing resources, utilization, CPU, memory, disk, and we also want to look at the throughput. So how many requests can this box, is this box able to generate against the application, the latency and the error rate. So the latency is actually the time it takes between sending the request to the server and getting the first byte of the response from the server. This defines the latency. We are also interested in error rates, because if we start pushing the load to the server and we get errors back, we kind of are in trouble, so we need to investigate what's going on. On the application box, we are also interested in collecting metrics related to CPU or to computing resources, CPU, network, memory, and disk. But in the case of a web server, we are interested in some more detail. So one metric we should be looking at is request queuing. Most web servers have an internal queue that queues the request before they get assigned to a handler and then dispatched. And as we push more load into to the server, if we don't have the server configured properly, this request queue might be filling up, and we should pay attention to it. Then again, we are interested in throughput, latency, error rates, and active threads. Some or most web servers use threads, so it's important to keep an eye on our thread pool. How many threads is the web server configured to use? How many of them are active, waiting for I/O? So we want to keep an eye on the state of the threads to see what's going on. Regarding database server, then again, computing resources. And then for the database server, it's particularly important to pay attention to swap utilization, because we don't want our database server to be swapping. We want to fine-tune it to use as much memory as possible, but to avoid using swap. And then we are interested in some metrics like queries per second, query plan cache hits and misses, because the database server, every time we put a query running, it has to parse the query, calculate the execution plan for that query, and the database servers usually keep a cache of the execution plans. That's why we always should be using query parameters instead of just composing the queries with the parameters inside the query. And this is usually a cause of bottleneck in the database server. Also, we should be looking at index misses. So if we are pushing queries to submitting queries to the database that are not being optimized by indexes, we should know about it. And also read and write logs to pay attention to what's causing contention on the database and the access to the tables. So what about when we are preparing a load test plan? How should be our load generation curve? There is, for instance, JMeter supports various scenarios of various configuration of load generation curves. You can have the basic, which is fixed number of users. So you start your plan with 100 users making 1,000 requests each user. That could be a plan. Usually I prefer this kind of curves where we start low just to warm up. So we start with one user generating moderate load to warm up the server, and then we start increasing the number of users progressively. And then when we reach the highest number that we planned for, we keep that amount of users for longer periods. Something like 10 to 15 minutes would be okay, so that we can see, we can track progress of how will our application behave under heavy load for a longer period of time. So usually I try to use, especially in almost near production scenarios, I tend to use this curve because I want to see how the application will scale as I push more load into it. So about metrics. What's the end game of the metrics? Why are we running this load test? Because we want to know how our application will scale, but we won't know that until we find out about metrics, right? So our end goal is really to maximize the throughput. We want our application to handle as much requests as possible. We also want to minimize latency. We want our requests to be answered fast. And then again, we are looking at the low average and low standard deviation because we want some kind of consistency within the application. So I don't want my application in the next 10 seconds to respond to like 2,000 requests per second. And on the next 10-second slot, it will bring down to like 10 requests per second. So we want to keep the lines as smooth as possible. Also, we are looking for 0 errors. The application, this is kind of wishful thinking, right? But we should struggle to keep the error rate to 0 as much as possible. And we're also looking to minimize resource utilization. So my application should serve as much requests as possible within the minimum time possible and utilizing the minimum amount of requests possible. So about tracking performance. So we are preparing our application. We run the load tests. Everything is good. We push it to production, and then we make changes to the application. So it's important to periodically run the load tests again and keep track of the values of the results among every iterations, every runs, so that we can track if the changes we made to the application are making performance worse, better, or at least we are keeping it. So it's important to keep track of this and run these tests periodically. In order to make the results comparable, we have to have some invariance, right? So this infrastructure should be always the same between every runs. The database sizes should be always the same, and the load generation pattern should also be the same among several test runs. So this is to make the load test results comparable. Okay, so let's look at a demo. So I have here this very basic ASP.NET MVC application. This is a simple messaging application, very simple. So what's happening here is that, well, it's MVC. What's happening here is that this is a web application. It has a database, SQL server, with very simple data models. So I can log in. All the data is fake. When I log in, I have my inbox, which are the messages sent to me. And this is simply providing a list of messages, and then I can click and see the detail of a message. So an important detail here. Notice that when I go to check my inbox, the columns that are presented on the list are the sent date, who sent the message, the subject, and then a link to view the message. And only when I click the message, I have the message text, which is a larger text block. Right. So for you to have a clue of what's going on here, let me show you that the database is actually currently populated with about 4 gigabytes of data. So it's not this kind of database that we as developers just push some data into it. I actually took the work of creating a tool to populate the database with this amount of data. Okay. So let's go to JMeter. So who has seen JMeter before? Okay, a couple of hands. So this is the graphical user interface of JMeter. It's where we design our test plans. So this is Java. This is a Java application. So what's a test plan? When you create a test plan, you have these two nodes, the test plan and the workbench. The workbench is something to store variables to be used within the load test. But what we are interested in here is the load test plan. So let's go quickly through the test plan. It starts with this controller, HTTP request defaults, which provides the default values for every HTTP request that will be used on the test. So we usually use this to set the server and the port that will be hitting within the test plan. And then we have the thread group. The thread group is the element that will determine how many users will the test plan have in concurrency and how many requests will each user make. So this is the simplest case that I mentioned earlier. There are more complex, but for the purpose of this talk, I will use the simple. And then we start having the elements. So what this test plan is actually doing is for each user, when JMeter starts a new user, it will run these steps that are under the only once loop, the only once controller. And what this is performing is very simple. So the first time a user is started to generate the load, it will make a call to the index, to the login page. It will post the login information to authenticate that user. Then it will hit the index page, and then it will start looping through the inbox controller. So let's see where it takes us. Here, then we have some nodes that are collecting data for us. So this one is the summary report, where we check the metrics of how the test is running, how the test is performing. So we can see that the inbox is at about 240 requests per second, with answering in about 370 milliseconds, and with a standard deviation of about 100 milliseconds. So it's kind of not bad, not that good, right? So let me stop the test, see here for a while. So JMeter has support to generate several graphics. So let me give you some examples. So this is the Percentiles graphics. So for each, it's drawing the percentile line of response time for each controller. Then we have several others, which are the request time, the time it took to get the response over time, and transactions per second. So it gives me a lot of metrics about what's going on. We'll be focusing here on the summary report. So just to give you an example of some optimizations that we can run, this second test will hit a second endpoint which will serve exactly the same page. Let me show you. It will hit this inbox to endpoint, which is exactly the same page as the inbox, but with an optimized query. The first query is simply performing a simple query using the ORM framework, the entity framework, and it's getting all the data from all the tables, and this inbox will just collect the columns that I'm interested in to render this page. So this is the kind of optimization that we would be doing on a production system. So this is the line we are interested in. So we can immediately see that the average response time went to half, about half, and we are performing much better and in terms of throughput. So I'll stop the test. So throughput is now at about 550 requests per second just by optimizing the query to render that page. Okay. A third example, I'll comment this and activate this. A third example, I have a third endpoint that is actually rendering the same page, but it's using output cache. So output cache is a mechanism of IIS, but other web servers also have it, which is the ability to cache the HTML served by an application server, keep it cached and serve it from the cache until it expires. So in this test I'm using it. Let's see where it goes. So it already went fast to the 2,500 requests per second, and with average response time of about 30 milliseconds. So remember, all of this is running on my laptop. I can show you here. So opening the task manager, you can see that my CPU is saturated at this moment, mostly by IIS, which is handling the load. And then here, this is Java coming in second place, which is the load generation tool that is working. Okay. On the normal scenario, it's important to notice that on the normal scenario, I would be running the load test using a console application instead of the graphic application, because the graphic application is consuming resources that I actually shouldn't be doing that. So summarizing here, we went from an average of 350 milliseconds in terms of response time to about 30, so that's kind of a factor of 10. Okay, so back to the slides. Now let's take a moment to talk about average event statistics. The issue, let me give you an example from another load test that I once run. So in this load test, we got a minimum of 54 milliseconds, which is kind of meh. 54 milliseconds as a minimum. Not bad, not good. But we have an average of 761 milliseconds. So average of 700 is kind of not a very good number for a web application, and then we get this maximum of 2,200 milliseconds, but the standard deviation is 900. So pay attention to the difference between the average and the standard deviation. So standard deviation is greater than the average. So this is a huge indicator that something is not going right in our application. So this is the actual graph of the response times that was generated by that test. So you can see that it's always up and down, up and down, up and down. And it's important to notice that JMeter, as many other tools that analyze load test results, produce these graphics by sampling. So what happened is JMeter, when he got the timer to produce a data point on this graphic, it went by sampling. So just to plot, the average line is there. Okay? So there are lots of stuff below the average line, lots of stuff under the average line. So we are usually more interested in percentiles graphs because percentiles are more meaningful than averages. So this is once again the same percentiles graph for the load test generation, that load test. So we can see that we have a 50 percentile of about less than 100 milliseconds. So this means that half of our requests were responding in less than 100 milliseconds. And then we have this big jump around percentile 63 to 68, where you can see this big jump. So we kind of suspect that there is something going on here. Distribution graphs are also interesting because it allows us to understand that, well, I have pretty much significant number of requests that were responding in the range between 0 and 100 milliseconds. Then it drops to 100 and 200. And then I have this long tail here of some percentage of requests that were responding in 2 seconds. But you only get what's going on once you plot the real data. So this graph was plotted using R, just importing the data, the output data of the load test, and plotting the data, so you can immediately see that there is this amount of requests that were responding very fast, and there was all these requests that took just too much time to be responded, and there is nothing in the middle. So here I've just put on the bottom of the slide the instructions, the R commands to generate this graph for future reference. So you really have to plot the data to see what's going on. So, common pitfalls. Regarding the database engine, common pitfalls that cause the application to run slowly usually are missing index. So we have queries that don't have any support of index in the database. Queries that are not optimized, read or write log constraints, disk I/O, and connection limits. Connection limits is also an important deal because it's very usual to install database servers and web servers with the defaults, and most of the times the defaults are not production ready, so we need to keep an eye on the collection limits and thread limits. Regarding our application, most common causes of slowness: unoptimized code, compiler options for those who use compiled code, lack of cache. So it's important also to keep track of what could be cached in our application to avoid unnecessary calls to the database or to services. Thread pool limits, connection pool limits. So once again, the connection pools are important because if we have our web server attending 1,000 threads and the connection pool is limited to 10 connections, well, it won't scale as it could. And undisposed TCP connections. So this is kind of a lesson learned from a project where there were connections being opened, HTTP connections being opened, and they were not being disposed. And after a while, we ended up the server with lots of sockets in closed wait state, and it would just refuse to open more sockets. And regarding operating system, we should also be looking for the limits for file descriptors or sockets, timeouts in closed wait, and the max buffer size of sockets. This is especially important if your application demands some huge or high high payloads from a service. For instance, a video application, you should pay attention to the buffer size of TCP because you probably want to have larger frames. So, to summarize, we should test our application under load before users or the internet will, right? So that we know ahead of time how will it respond to scale and if we are comfortable with the load that we predicted or not. I know this is better said than done, but still the advice. You should also find bottlenecks on the application to get to know where the application what's the root cause of the slowness of the application, or what are the bottlenecks, and to check if we can fix them or not. Iterate and measure the results. So we should struggle to keep improving our application and measure how our changes are affecting the performance. And use the statistics for smells, but plot the data for the details. This is very, very important. Some tools some load testing tools, the more simple ones, will just outcast you some statistic, and the statistic will not tell you everything. So use the statistic for detecting smells, but then you probably have to deep dive into the details to see what's really going on. So that's it. Any question? Thank you. Any question?
Hi.
Hi.
So one big problem that we have often when we plot latency data is when we see bad latencies in multiple places.
When we see, sorry?
Bad latencies in multiple places. Do you have any technique or suggestion to understand what can be the cause and what can be the consequence? For instance, if you see one component with high latency and another seemingly unrelated component with high latency, are there any techniques to understand what is causing what without looking at the logs and trying to time everything in a very fine-grained way? Thank you.
Okay. Let me go back here. So in that situation, I'm assuming that you have this component that calls this other component, or might, yes, no? Okay. So one thing that's important to track when you are in a situation that you have several components running on several boxes is to be sure to collect metrics on all boxes. So you can use tools like New Relic, application insights to try to collect metrics from the machines, so that you can try to investigate what's going on behind the machine. So, for instance, if you are hitting a web server that calls a web API server, and you have latency on the web API, the latency on the web API will propagate to the web application, right? So this kind of stuff tends to propagate. Equally, if you have latency on the database and you have the web, then you have the latency on the database propagated to the web API and propagated to the web application. So, first tip, I would probably collect the metrics from all the boxes, and if I see some high latency, I would track down which node is causing the high latency, and then investigate from there what could be the potential causes of that high latency, but try to see where the high latency is coming from, the source of it. So that's kind of the challenge. It's usually you have the tools right out of the box to determine where the high latency is coming from. The challenge is determining why, and that comes out of investigating the technology that you are using in that box. What's causing the latency? If it is a database server, what is the root cause of the query. So probably you want to inspect the queries that are running, try to detect the slowest queries, and then check the execution plan to see what's causing the slowness. This is in case of a SQL query. So the answer is kind of depends on your scenario. Did I got the answer? Okay. If you have any follow-up questions.
Yeah. So suppose this concrete example where you have your injector, your data injector into the system, that sometimes sees some latency spikes, and you also see the latency spikes inside the system.
Okay.
How do you tell if the problem is on the injector or inside the system? Where it doesn't seem it should be nowhere.
You have to have metrics for that. You have to be able to collect metrics for both systems and try to isolate the problem.
So you'll always end up digging in the logs and the code and so on.
Not if you have instrumentation. So if your application has proper instrumentation and is emitting metrics, you won't need to go through the logs. That's an important premise of all this, is that you really have to have metrics so that you don't end up immersing yourself on logs, which is very boring, right?
Thank you.
For instance, I know this better for SQL Server and SQL databases. SQL Server emits lots of metrics for everything, so if you know what you're looking for, it's very, very easy to find the source of the latency in SQL Server, because it just emits a lot of metrics. So you can have a strategy of, so you know the query that is causing the slowness. You run the query, see the execution plan. The execution plan might seem right, but if you start if you put that query to run in concurrency, you can look at the metrics, and usually it comes down to locks, read-write locks. So you can only find it because SQL Server is emitting these metrics, right? So it's very important to have proper instrumentation to try to find the root cause for stuff. Thank you. Any more questions?
Hi. What was the actual cause of that weirdly behaving application you showed?
Okay. You know the answer, right? So you mean this one?
Yes.
Yeah. I don't know. My best guess is that this was about I/O. This was probably and I don't know because we didn't have metrics. This was most probably caused by the tuning of the web server not to have enough threads and workers, and because all these requests were hitting the database, it was causing I/O. It was causing I/O waits, and it caused this kind of behavior where some requests would just get the answer and be responding back. Lots of other requests ended up on the request queue and waiting to be answered. That's the best answer I have.
Or just a bad instance behind the load balancer, for instance.
Sorry?
I meant, if the scenario involves a load balancer and 3 backing instances, it could be that just one of them.
That's not a scenario, because this test was run with a box generating load to another box running the web server, so there was no load balancing. There was no load balancer in it, and it was done on the local network, so there is no internet in the middle of anything. So this was local. So this was caused by runtime. I'm sure about that. I'm not sure if it was like threading stuff, connection pool stuff, web server configuration stuff. Not sure about that because we missed the metrics. Anyone else? Any further questions? Okay, so let's call it a day. Thank you.